We want to extend our analysis of this kind of idea of linked equilibria where they're not immediately cooked into the reactions. We need to look at different reactions together. We saw that solubility can be affected by other reactions, right? Magnesium hydroxide is a base. So if we add acid to a solution, we can get an increase of its solubility. Now, it's easier to predict because of hydroxide in there, right? Hydroxide's already in the solution, or in the equation, because it's a part of magnesium hydroxide. So it more directly kind of links into what we already know about acid-base chemistry, the hydronium hydroxide relationship. But this effect of solubility is generally true, that a basic salt will always have increased solubility at lower pH, and acidic salts increase their solubility at high pHs. Generally, a basic salt will react with the low pH of an acidic solution, and an acidic salt will react with the high pH of a basic solution. So this is always true even for salts that don't feature hydroxide. And the question is, how much is this solubility going to change? Let's take a look. How is the solubility of lead-2 fluoride, PbF2, affected by solution acidity? The KSP of PbF2 is 2.7 times 10 to the negative 8th.
All right, so I want to know how the chemistry of lead-2 fluoride dissolving is affected by acidity. Okay, and so what we want to think about is, well, how we can start kind of this process is like, well, what happens when we dissolve lead-2 fluoride? Right, what would that look like? And we know we have our PbF2 solid would dissolve, get the Pb2 plus, and we'd get the 2 fluorides. Okay. Well, if the lead and the fluoride dissolved in, say, an acidic solution, what would happen there? How would that drive the dissolving, okay, or affect dissolving? And really what we'd be asking is, how would that interact with either of these ions? Well, lead isn't going to do any acid-base chemistry, but fluoride is a weak base. Right? We know that fluoride right here is a weak base. And so we would expect that that can react with acids. And in the kind of trade, or the kind of the molecule that is driving solution acidity is hydronium. So what can happen is the fluoride could react with some hydronium that's dissolved in solution. And this would just be a Brunstad-Lowry acid-base reaction. So we can predict it'd be HF plus water. So if we dissolve, we'll make lead and fluoride ions, and the fluoride would be able to react with any hydroniums that are present in solution. We know that in pure water, there's not a lot of hydroniums, so this chemistry still happens. This chemistry happens in every single solution where there's fluoride. But there's not a lot of hydroniums in water, so this doesn't really happen. It doesn't really matter as much as, say, the reaction of fluoride with water. And so this doesn't really matter, but if you start to have an acidic solution, there's more hydroniums, and this reaction is really going to start to matter. This is really going to start to kind of be happening as the concentration of hydronium comes up. And we know that when you dissolve, say, 1 mole of lead-2 fluoride, you get 2 of these, or you get 2 fluorides. So this reaction would happen, so you can finish that word, reaction for each fluoride, right? So that'd be a times 2. So we can think about kind of the overall chemistry that happens when we dissolve. We can put it all together to kind of see what overall goes on when you dissolve lead-2 fluoride in an acidic solution. So we know we'll have the lead fluoride is going to dissolve. You're going to get the Pb2 plus aqueous plus the 2 fluorides. We know then that one of those fluorides is going to react with a hydronium, acidic solution. So that's another reaction equilibrium, and you're going to make HF plus water. And then again, another fluoride. Right? We got those 2 fluorides. Both of them are going to react. We know acid-base reactions happen one at a time. And so that is then make HF plus HO. And so this is the overall chemistry that's going to happen. All of those processes are going to happen. The lead's going to dissolve, and those fluorides would react with the acidic solution. And so we can put this all together. PbF2 solid plus there's 2 fluorides plus the 2 hydroniums. That's an equilibrium. There's lead cations plus the 2 fluorides. 2 HFs plus 2 waters. We can go through and cancel out the fluorides to show up on both sides. Right, that's kind of like the intermediate here. Fluoride is produced and then it reacts. And so those would cancel out. And so the overall chemistry that we're looking at when lead 2 fluoride dissolves in an aqueous solution, we get the lead and 2 HF and 2 water molecules. So this, when we talk about how is the solubility affected, well, one, it's an entirely different reaction. When you have lead 2 fluoride reacting with an acidic solution, you're making lead cations, hydrofluoric acid, and water. Right? So this is a functionally different process. It's not just dissolving and producing. You'll note there's no fluorides here. So KSP does not describe this process. So what does describe this? What is the equilibrium constant for this process? Well, we know it's made up of these 3 component reactions. So if we could multiply those together, we'd be good. So this first reaction, we know that's KSP. So that one we do have is 2.7 times 10 to the negative. So what about this reaction? Fluoride reacting with hydronium, hydrofluoric acid, and water. That certainly looks like one of the types of reactions that we dealt with when we were talking about acids reacting with water. HF is a weak acid doing stuff in water, and you'll note HF reacting with water to make fluoride and hydronium. That's a reaction we've seen before. If we have HF aqueous reacting with water as a liquid, in equilibrium, make an F minus plus H3O plus. This is described by Ka. Right? That's just a reaction of an acid with water. The equilibrium constant for that is Ka, the Ka of HF. Right? We can look that value up. The equilibrium constant is 3.5 times 10 to the negative 4th. So what we're dealing with here is fluoride reacting with hydroniums. So this is going to be the reverse reaction, which means the K is going to be 1 divided by Ka, right? We're just changing what we call reactants and products. So that would be 1 divided by 3.5 times 10 to the negative 4th. So we can see that our overall reaction is the KSP. The K for this is going to be 1 divided by the Ka of HF, 1 divided by the Ka of HF. And so our overall reaction is PbF2 plus the 2H3O plus and so the K for this reaction is going to be my KSP of the lead fluoride times 1 divided by the Ka of HF times 1 divided by the Ka of HF. I'm doing these steps 1, 2, 3. So I just multiply all of those equilibrium constants together. I plug in those numbers. That is 2.7 times 10 to the negative 8 times 1 over 3.5 times 10 to the negative 4th times 1 over 3.5 times 10 to the negative 4th. And we get that K is equal to 0.22. This doesn't get a fancy name, no sub. It'd be like a KC. We want to call it the KC for this reaction. Just the equilibrium constant describing this equation. And so the thing that we can see here is this is still less than 1, but you'll note the KSP was 10 to the negative 8. So in pure water, lead-2 fluoride barely dissolves. Really low solubility, you barely get any dissolution. Now all of a sudden you're looking at 0.22. Okay. This is a much higher number. So lead-2 fluoride is much more soluble in aqueous solution. All of a sudden it is possible to get the lead-2 fluoride to dissolve. Another important aspect of this is that we have a reactant hydronium here that shows up in the equilibrium constant expression. It also means you can start to drive this equilibrium using Le Chatelier's principle. You can add more reactant and get more shift to product, which would mean dissolving. So if you make your solution really acidic, you can get all of your lead-2 fluoride to dissolve. This is kind of what we saw previously. When if you take any sort of salt that is basic, and you put it in an acidic solution, its solubility greatly increases. It's going to really increase. It's really going to drive that solubility. You're going to see a lot of that. And so that's why K goes up, right? And this is in general true. And you can start to see why it's going up. It's going up because you made the solution acidic, or because it's reacting with an acid. If you put a lot of acid in there, you're going to get a lot of reaction. You're going to see a lot of dissolving.
So we can see that with this lead-2 fluoride, because it is a basic salt, if you make your solution acidic, it will have an increased solubility. We can see our equilibrium constant for this dissolution in an acidic solvent. It's now 0.22. It's still not great, right? It's less than 1, but importantly, it is much higher than 10 to the negative 8th, right? So you have a lot more dissolving, a lot more of your lead-2 fluoride is going to get out into solution. And again, this is what we would predict with Le Chatelier's principle, that if you were trying to dissolve lead-2 fluoride and you put an acid in there, fluoride is a weak base, so it would react with the fluoride right here, if I can get it. The fluoride is a weak base, so putting in the hydronium, we can think of, or increasing the acidity, reacts with that fluoride. You're going to shift to products to replenish it. More dissolving is going to happen. Let's look at some diagrams of what's happening. So PbF2, we're going to try to dissolve it in pure water, which is what KSP defines, and not much happens, right? KSP is low, saturation limit is low. There's not much Pb2 plus or F minus floating around in your solution, right? It mostly stays in the solid. But we can change our solution by making it acidic. And now there's a new reaction that is possible. The PbF2 dissolves in the presence of the hydroniums, right? It's an entirely new reaction that we've got here. And this now has a much higher equilibrium constant. So now the PbF2 dissolves and we also get the products of HF. That's important. We now have a solution where there's HF floating around out there, as well as the Pb2 plus. So importantly, we've gotten the solid to dissolve. The Pb2 plus is floating around in solution. We have not increased the amount of fluoride. There's not free fluoride floating around in solution. Instead, it's an HF molecules that are floating around in solution. So what we have functionally done is led to more dissolving. We've gotten solid out of the, to dissolve out in solution, and we haven't changed the underlying equilibrium constants, right? Pb2 plus and F minus don't want to be floating around in solution. They're just not, because there was the acid present for the fluoride to react with, is basically what happened. So this sort of increased solubility is true for any salt that's basic. So one application, one place where we see this, is that coral, like in coral reefs, is made up of calcium carbonate. That's a primary component of the structure of those animals. And that is not very soluble in neutral water, right? 8.7 times 10 to the negative ninth for the KSP. That's pretty low, not really dissolving. But this idea, this pattern of dissolving in the increased dissolving in the presence of acid, where basically the anion reacts with the hydronium. In the case of calcium carbonate, the equilibrium constant becomes 180, right? Pretty high. And so what ends up happening is if the ocean is not acidic, the calcium carbonate of the coral atoms will not dissolve. So then you get, living coral. If the acidity of the ocean, the acidity of the solvent that calcium carbonate is in, gets too low, all of a sudden the calcium carbonate starts dissolving, and then the coral animals fall apart, right? The little parts of their bodies just start dissolving, and then the animal dies. And that's how you get coral bleaching, where basically the reef is just dead. There's all the animals have died because basically their bodies just dissolved. So the effects of that sort of these solubility is very, very sensitive to pH, right? We're going from 10 to the negative ninth, which is not dissolving at all, to 180, which is really dissolving. And it doesn't even have to get all the way, you don't have to have a ton of acid present, super low pHs for this to start mattering. Where it starts driving the solubility, increasing that solubility of the calcium. That calcium carbonate is starting to dissolve more and more in the solution. Let's look at another thing. What is another salt? How is the solubility of lead 2 chloride affected by solution acidity? KSP for that, 1.6 times 10 to the negative fifth. Well, PbCl2, very similar to PbF2. It's going to follow the same process. We can write out our description for actual dissolving of the salt, right? Getting it to break apart, low KSP. We could think, well, each chloride, that's my anion, that could react with my hydroniums, right? A chloride with hydronium, we can make HCl and water, just, an acid-base reaction. And this would need to happen twice, right? Because I'm making 2 chlorides, right? Which I can see is the same thing right here. We've got those 2 chlorides, so it needs to happen twice. All right, same idea as what we saw with PbF2. So my coupling, or my kind of set of equations, is going to be the PbCl2 dissolving into the 2 Pb2 plus and 2 chlorides, and then the 2 chlorides reacting with H3O plus to get our overall reaction, determine the Kc for that, and once again, it's going to be the equilibrium, the solubility product divided by the acid dissociation constants of HCl. But wait a second, our resulting Kc is lower. And that's because HCl is a strong acid. So because HCl is a strong acid, that means chloride is not a base. So chloride here is not a base. And so this ends up not being an acid that we would predict have its solubility changed. So it's not always true that acids, things become more soluble under acidic conditions or anything like that. Instead, it doesn't happen. And this lower equilibrium constant doesn't mean the solubility decreases. It just means this reaction doesn't happen. This idea of PbCl2 reacting with acids to then generate the Pb2 plus and the HCl. Instead, the original solubility is the one that happens. This is still the dominant process for PbCl2 to dissolve in an acidic solution. All right, another video down, no participation 320 questions. That is kind of the meat of some of the solubility stuff. We got one more topic for chapter 15, got 2 videos about it. I'll see you there. And solubility comes up into that one too. It's all linked. Couple of equilibria, right?